So yeah, hello everyone. So as I've been introduced, I work with a specific application of battery transportation, which is aerospace. So everything that flies. As you can understand, this is some kind of premium area in which battery are thought of being utilized. Here is where we are looking for the best performance possible in order for electric aircraft or hybrid electric aircraft possibly to take off. So energy storage for air mobility, as everyone knows, we are committed in trying to abate the carbon emission. One of the most difficult sector to decarbonize is the civil aviation, because we already have a very good technology with current aircraft and gas turbine engine, which are fairly efficient, but still rely hugely on hydrocarbon. The EU has put forward targets for emission reduction in order to reach carbon neutrality in year 2050. The reduction of the aviation emission is not easy and passes through three main streams. The first one is the use of sustainable aviation fuels and economic measure. For those who do not know, CORSIA, I don't know how to pronounce it, is some kind of is a set of economic measure to penalize the production and use of aviation fuel, some kind of a carbon tax. Then a small part can come from the improved air traffic management and operation. So for example, the route that aircraft take today, or how to manage landing and takeoff operation at the airport. What mostly we work on is the remaining part, that is a combination of technologies. So both in terms of airframe, so more efficient aircraft, lighter aircraft, energy, so replacing the hydrocarbon fuel with something else, and system, having more efficient way of transform energy within the aircraft. The European, the EU, and the Directorate of Research put forward three strategic thrusts. I'm using their terminology, and developed three platforms on which electrification, or which new aircraft concept are supposed to be introduced. Actually, 3+1. The short and medium range, that are aircraft for 150 to 200 passenger. If you ever take a Ryanair flight, that's what we're talking about. Hybrid electric regional aircraft, so something smaller that generally accommodate 50 to 100 people, and hydrogen aircraft. Hydrogen aircraft, I will not go into details, but basically involves using liquid hydrogen for very long distance intercontinental flight, like Boeing's, I don't know, 777 or Airbus A340, A350. I come up with this nice graph. So on where those concepts are located, here on the x-axis, you can see what is called utilization of power. So how much electric power you need to move the aircraft. So 100% means only electric motors. Y-axis, you have hybridization for energy. So how much energy does your aircraft carry? That means as you go up, the more battery you carry. There is an area that basically is unfeasible, either because it's technically impossible or it just doesn't make sense to have a lot of battery and then use gas turbine for propulsion, unless your business model is to bring battery around. This is where we are here now, basically almost 0-0. The other extreme, that is the +1 I mentioned before, are the all-electric aircraft. Now, if you ever seen an article saying that 200 passenger aircraft will power by battery only, that's crap bullshit. The maximum that technical limit, that physics limits tell us that we can propel electrically only, are drones, eVTOL, also called air taxis, when they will be regulated and authorized, or very small aircraft, basically general aviation, like those trainer aircraft. If any one of you has a pilot license, mostly that's what you pilot. The first thrust is roughly here on this plot. That's the picture of what such an aircraft might look like. The amount of electric energy required here goes between 2 and 8 megawatt hours stored, and they will be mostly used for what we call secondary application. Secondary application means everything that is not main propulsion. So, for example, landing gear, taxi system, avionics, movement of the flaps. If you ever seen an aircraft at landing, they move the flap. They can be electrified, they are pneumatic. The hybrid electric regional are smaller, so allow to use the energy for side propulsion. Basically, the battery will be assisting the main propulsion system. And here, smaller size means smaller energy stored. So roughly here, 1 to 4 megawatt hours, still depending on the size. In the strategic document that you may access, they use the word technobricks. So those are all the technology that needs to be developed in order to make electrified aviation possible. Especially referring to the electric system, there are other, of course, that I don't include here. There is the generation and the storage. So generators for more complex system, fuel cell. We have some speakers here researching fuel cell. So this is a field of application. And of course, battery for storage. Then as we move towards the usage, we have conversion, inverter, converter, distribution, and loads. So APU stands for, is basically the starting motor that starts the aircraft. IPS, eye protection system, flap actuators, cabin loads. So whoever wants to watch a movie while flying or want to charge a mobile, that's a cabin load. And avionics. Currently, we use batteries, that is the main topic we're discussing here, for the last two. Sizing power of this aircraft, just to give you an idea of order of magnitude, are 5 to 40 megawatt for propulsion. Megawatt, 1 megajoule every second. Secondary system in future aircraft, of course, much smaller, 30 to 20, 50 kilogram, but still significant compared to today's standards. For energy storage, the clean aviation strategy consider both fuel cell and batteries. They are not mutually exclusive, but cannot be seen separate one for the other because they have different characteristic and they hybridize fairly well. So the fuel cell have the advantage compared to large battery system of being lighter. Battery system, if you look some preliminary calculation, we are talking about batteries that weigh 5,000 kilograms on an aircraft. Means 20–30% of the takeoff weight. Are lighter storage because they rely on hydrogen instead of, say, lithium-ion cells, and cope fairly well with other aircraft subsystems. On the other side, batteries are more efficient, and they have much less problem in terms of thermal management compared to a fuel cell. If you think about that, 50% efficiency of a fuel cell means that the other 50% becomes heat, and you need to dissipate that heat during flight. And response time, the batteries are not supercapacitor, but they are reasonably fast in response, for example, to a sudden power surge required. For example, if there is a missed approach, the aircraft needs to get power, full power immediately in order not to crash. Fuel cells here are much slower. They need time to build up their power delivery. So trends for battery research. Okay, this didn't go as intended. This is still programmatic document of view that Stefano and Roberto may have contributed writing, I guess, are identified short-term, medium-term, and long-term. And we have related to the aviation hardware integration and operation area where we want to work. So when it comes to hardware, so basically the cells, we want to have the new generation of battery that we will see later, what we call the generation 4 battery, the solid state, to use a more common word, which promise better energy density, better power density, better safety, and hopefully, unfortunately, still not verified, longer lifetime than today's. Lightweight modules and pack, thanks to techniques of involving additive manufacturing, for example. And for the long-term perspective, generation 5 cells, so advanced lithium, post-lithium batteries, still with the same target. When it comes to integration, the advanced integration, this mostly refers to sensor and management system of the battery. So you want to know what happens in all your 1,000 battery cells and making sure that all of the cells are behaving properly. And if something happens, that you have a safe way of, for example, excluding that cell. This is a huge step to do in order to get certification that is extremely hard for batteries. And since we're talking about certification, one of the things that are particularly challenged is that today there is no standard for certification of electric aircraft. Literally needs to be written, means to be invented. Probably some of you in future will be involved with this. And it's a quite active, I don't know if you call it research field or anyway, it's a field that still requires strong contribution and will require even more in the next, let's say, 10 to 15 years. Operational batteries. So development of certification standard, development of procedure, testing, definition, it may be surprising. And this is fairly new in research, but of course you can understand why it's important. Sustainability of the battery production and repurposing after they reach the end of the useful life for aerospace, and everything related to circular economics. One thing, cost, I haven't mentioned in the priority. This is because this aerospace is a premium sector. Don't get me wrong, it's not that we can spend billions of euros just to buy a single cell. So cost is important, extremely important, but it's not a make or die, like for example in automotive, where the cost is a priority. Or even if someone is involved or will be involved in marine applications, so battery for ships, what they want, low cost. After that, low cost. After that, long life. After that, low cost. There are also some transversal set of requirements that are set in the policies. So capability of fast charging, I will explain later why. So providing high power and low degradation at the same time, of course, for life. Creating standards for control and interfaces between battery system and power management and distribution or other aircraft system. Cross-compatibility, that means that you want to use different kind of battery without to repurpose everything else. Develop battery swap technology. Battery for aviation are not going to last 100,000 cycle. Reasonably will be 5,000 cycle, but this is very optimistic, most likely 2,000-3,000 cycles. So battery needs to be swapped and removed. There is also an idea of swapping battery in between one flight and the other. This requires developing connection mechanics, so the physical way of removing battery, the devices, the operations, electronics and battery management system for different chemistry, and developing all the infrastructure and logistic of battery swap, here including second life application. For example, a battery after is considered no more useful for aerospace may go into stationary storage, grid storage, may be used for naval application. there is a need of developing a supply chain, an infrastructure for this market, economic model for this market, techniques for determining performances of such battery in order that they don't explode if they are abused, for example, peak in demand of electric stationary power system. And then SOX, which means state of, it was a few years ago, state of health, now is state of everything, state of health, state of functionality, everything involving the knowledge of the properties of a battery. So what is the useful remaining life, if the battery degraded, if there is a leakage of chemical element, if there is a dendrite formation that may create safety issue, so on and so forth. So where are we now? Batteries, as I said before, are basically function of support of secondary system. Auxiliary power unit starts. The biggest battery today in aviation is roughly 1 megavolt ampere, 1 megawatt, and it powers the APU of the Boeing 787, the big one. Batteries are efficient today, at least compared to our aircraft system. 90% battery, I think everyone can agree on that. The best gas turbine makes 40% maybe, when in good condition. Other system even less. Diesel car, 35%. Flexibility, because they can be easily scalable. What today is not acceptable for aerospace is the weight and the safety. We have liquid electrolyte, which are flammable, and that's a huge risk. So just if you remember, a few years ago, there was a problem of the batteries of some electronic device who caught fire in the aircraft. Now just imagine if it's a battery that is 3,000 times bigger, that takes fire, see what happens. And integration with our other aircraft system. Current generation, for those who are not familiar with this, are labeled generation 2B, that are battery whose cells have NMC as a cathode and silicon carbon anode, basically carbon anode with very small content of silicon, and liquid electrolyte. Those cells are the standard for automotive industry, and basically their development has been driven by the automotive industry. For example, take the Tesla or take the Chinese car manufacturer that are launching into the market now. They are here. They are approaching the generation 3A, that is basically an improvement of generation 2 battery. There is not a significant difference. The only thing is that we go towards more energy dense anode and cathode. So we increase the amount of nickel at the cathode, while the anode sees an increase of the content of silicon, on which some colleague of you are working. This is mostly to increase the energy density of the battery, to make them perform better. I use the cell ZD because this is the main metric that you will see in aerospace. Basically, energy per unit of weight. Light, 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 or energetic, energetic, energetic. Other things counts much less. As I say here now, there is a gap. So far, cells have been driven by automotive requirement. Now, automotive requirement cells reach performance that are fairly decent for common use. As you see, electric vehicles are booming. Therefore, means that the cells for automotive industry are started focusing on things that are relevant for the automotive industry: reduction of cost, improvement of the manufacturing processes, increase of cycle life. And here there is a divide. Aerospace needs to start building their own cell type, their own manufacturing processes, their own techniques for parameter estimation. Here you have a wide background. All of them may have a role, and all of them may develop in research areas that are specifically to aerospace and will address mostly the aerospace market. I took this from a chart, so don't take this this judgment as a standard, because there is, again, here there is, even in aerospace, there is not a solution is good for everything. The importance of the weighting depend on the application. This company here wanted to have small aircraft for like 5 to 8 people, basically the size of a business jet. So, for example, they care a lot about life cycle for IC rate. But the main driver for improvements of aerospace specific battery are, of course, Her Majesty, the energy density, the cycle life for high C rate. C rate, for those who are not familiar with that, is a measure of the current that it takes to discharge a battery. 1C means that you discharge a battery in 1 hour. 2C means you discharge a battery in half an hour, 30 minutes, and so on. Anyone can tell me why this is important for aerospace? So for drones, they have a short range. So they complete their mission in a very short time. 20 minutes, 15 minutes, 30 minutes. That means 2C, 3C of C rate. For larger aircraft, if you ever take a flight, take the classic Ryanair flight, their business model is to keep the aircraft on ground for the shortest time possible. That means that when the aircraft is on ground and the aircraft has battery, if you want to keep the current business model of airlines and airports, you have 30 minutes, 20 to 30 minutes to charge a battery. That means 2C, 3C in charge. Then safety, of course. We don't want the aircraft that start falling from the sky. That value is what EASA, that is the European Association, the European Agency for Safety in Aviation, consider acceptable in types of serious accident of a system per hours of flight. So they say, if you're not able to ensure me that your propulsion system or your aircraft has one critical failure every billions, 1 miliardo in Italiano, hours of flight, nope, no way, not accepted. We don't even start the discussion. And operating temperature, of course. Now, again, the vision for aero batteries is that new generation of batteries will still be efficient, flexible, will be safe, thanks mostly to the replacement of the electrolyte. The weight will not be a showstopper, but will be still a limiting factor, but can be manageable. And this leads to new generation of battery. So the 3B, that is basically a continuation of generation 3. They are considered enabler for air taxi, so electrical, vertical, and takeoff landing aircraft, and commuter aircraft, so very small aircraft. Generation 4, basically known as a solid-state battery, where, as I say, they replace the liquid electrolyte with a solid or hybrid with ionic liquid compounds. This is not flammable, and this is important because basically means that it cannot catch fire. And it's a huge improvement in terms of safety. And is thought to be an enabler for hybrid electric aircraft at different scale. Fifth, lithium sulfur or lithium air battery. This is still too early in the development. We are here at TRL, I guess, no more than 3. And they are considered a long-term solution and definitely will not be seen operating before 2050. That is basically our most important time frame. Challenge for aero batteries. So yeah, no one fits them all. Not only one type of cell needs to be developed. This chart shows that, if you can read it, of course, I don't have a pointer, but the message here is that you can have cells that have a very good energy density, gravimetric, so they store a lot of energy for their weight, but they're not good at power delivery. Or the opposite. You have either one or the other. Of course, the research trend is trying to push towards the top left. Sorry, for you is top right of the chart. So we have these are basically one of the most state-of-the-art batteries that are available and produced. So this is not research, this is under production, product under production from the energy and from power cell. I explained before the C-rate capabilities, what it is. Drones are more power-intensive application than energy-intensive application. And of course, cycle life system is not seen in this graph, but of course, batteries need to ensure 2,000 to 5,000 useful cycle without fading. And now this is one of the areas that people are working on. For example, solid state today lasts few hundreds of cycle, but there are ideas and solutions to increase this number. This is the target that is considered acceptable. The good things is that the market is very active. So new prototypes come out literally every year. This graph is what of 1 year, 2 years ago. In a couple of years, they will be outdated. There are companies that are producing innovative cells, state-of-the-art cell at scale in gigafactories, and the new cell, let's say generation 3 cell, are expected to reach a production of gigawatt hour globally in no more than hopefully 3 years. Again, even this, if this is not the biggest market. So the automotive drives, but aerospace market is emerging as an interesting niche for premium cell. Why this is because of cost. Roughly to give you an idea of magnitude, aerospace application are okay in accepting a cost at cell level 5 times, maybe even 10 times the automotive. They literally worth their weight in gold almost. I added these slides following yesterday's introduction for Stefano. Don't worry about too much about the dots, just look at the color. The development roadmap are such that at the moment, the global leader are US and China. In the chart, as you can see, the Chinese development in red, the American in blue. Chinese are serious about this. We have colleagues that are in contact with some Chinese manufacturer. So these numbers are not just bullshit to impress some PR. They are able to reach 500 watt-hour per kilogram now, although at a low current, must be said. And I don't know for how many cycle, but there is basically no doubt in the scientific community that they will become the standard. So what we need, Europe. People like you, European researcher, because there is here a gap, and Europe, if wants to maintain a strategic leadership as the forefront of technology, cannot be left behind. So challenges for aero batteries. The priorities are, of course, at cell level, the weight and the performance. At cell and system level, the safety, basically as much as the energy density. Fault tolerance, already mentioned. They, of course, they need to survive operating condition typical of aerospace application. So low temperature, high temperature, humidity. At the system level, it's important to ensure the global standard and certification system. Supporting needs, already mentioned, manufacturing techniques, integration with other aircraft system. For example, think about the electric insulation. Here we're talking about kilovolt, kiloampere at the same time. In things that go in the air, where the air density is much lower, so it's much easier to have electric arching. So what we do about that, I will need the help of the people in front. Here at AAT, we are basically taking the battery research for aviation, either by developing innovative cell, so Gen 3 and Gen 4 cell, in terms of pure like electrochemistry, where people that work in the lab to synthesize material, test cell, destroy cell, that is very funny. And what I do is developing numerical tools for aeronautics. So basically computer simulation, we exchange data from the experimental people. Of course, one of the research trends, I will not spend that much time on that because it's not my specialty, and you have colleagues working on solid state battery, you can ask them all details. Still here is not clear what will be the solution. There are several materials as candidate for electrolyte. Each of them has pros and cons. The optimal balance needs to be found and cell need to be tuned. This will happen in the next year. Most likely the composite electrolyte will maybe a way forward, but honestly, I don't know. This may change really if some materials are found. Oops. This is the first sample that I brought you. You can circulate it. When I mentioned before integration, I'll just let this thing appear. So this is a prototype Gen 3 cell, if you can circulate it. That this is developed for an automotive project, but the concept remains true also for aerospace application. So the idea here is to integrate sensor in a cell so that the cell is able to control herself in some way. The electronics of the cell receive information for the sensors. So current signal, voltage signal, temperature, strain gauge to measure the deformations, moisture in order to see whether there is some risk for the electrolytes. This in order to improve our knowledge and the system knowledge of what goes on in a cell, and apply techniques for optimizing, for example, the extraction of energy from certain cell and not from other cell, for example, or to identify the best management strategy of huge battery cell pack. An innovative concept for mobility here is what we call structural batteries. So existing cells have a limit. The limit are that the development is reaching the theoretical maximum values achievable, but still the performance are insufficient for our aerospace application. There is a cell-to-pack penalty. The energy density at a cell level is different from the pack level because you have all the metallic frame, you have all the electronics, you have the cooling system, you have the thermal management system, you have the chips, you have the electronic board. From a performance point of view, that's added weight and gives you nothing in advance. So there is low integration. And again, no synergies. Those are cell, period. They don't do anything else. So the idea is, why not having cell that do also something else? For example, a cell may both store electric energy and carry some mechanical load. And this goes under the name of structural or multifunctional battery or multifunctional energy storage. This is an idea that first was a source for automotive, but is gaining traction also in aerospace. And we as ATAT were hugely invested on this research line. So here the idea is to get a system weight level reduction by combining different functionality. It's the same idea of combining batteries and hydrogen for storage. You combine different technology in order to get the best from each of them. There are here 4 levels of multifunctionality. That's not very important, but anyway. For example, you can have 0 level, that is what we have today on the top. Basically, a normal battery pack. There are cells here. There is a structure here. They don't communicate. The more you increase their interdependence, the more you move towards the full functionalization And the bottom picture, there are some research sample not produced by us. Look at the reference for the picture, where they have those filaments that store an electric energy and are basically based on carbon fibers. The rationale here is that, as you can imagine, there is a weight penalty. The more you move from the electrodes towards the pack, that can be quantified 40% mass and 60% volume penalty when you have your full battery. I will skip here the number. Roughly, you can have, at least theoretical, at least from our simulation study, a significant improvement in delta GD. Delta GD is the energy density per delta kilogram, not per kilogram. That means, in order to make it understandable in an easy way, you start from a panel, composite panel, you remove 1 kilogram, and you replace it with some kind of structural battery. So you removed 1 kilogram material, you added some other material that also gives you energy storage capability that you can measure in watt-hour. So theoretical simulation show that you can get potentially up to 1 kilowatt-hour per liter or per extra kilogram, which is theoretically twice the value of the cells that we consider advanced, let's say the solid state, that roughly have 500, if alone, of course. This just shows you where we are in terms of density. Add 1 to the figure because they used 0 as a reference point. So unfortunately, the composite panel are not lighter than water. So just add 1. As you can see, if you see the difference in between the yellow rectangular, you can see the penalty that you have when you go from cells to pack. As structural material, we generally use carbon fibers. Here, their different level of integration bring a different value of density. Solifly cell, I will circulate it in a few minutes, is one of the first prototype for structural battery that we created. Next generation structural battery cell have the potential of going towards higher density simply because they use much more energetic material and they are more structurally integrated. This is the result of some performance level where you can see how things start getting interesting if you are able to reduce the density of structural material to a value that is not too far from the density of the carbon fiber. So in the chart here to the left, when you go 0.6, 0.7, 0.8, you see how your gain increase exponentially to the level that a structural battery becomes more efficient than having a structure here and a battery here. These 3 curves basically come from our research project. They're called Solifly, Matisse, and some hypothetical future project. Solifly is a project that closed 1 or 2 years ago, whose output you will see soon enough. Matisse is an ongoing project that basically expands the purpose of Solifly. Here it comes the Solifly sample. I'll start it from this side. Don't worry, there is no charge here. It's gone. Just make sure not to get hurt with the carbon fiber who is delaminating at the bottom. So this is the cell. Is capable of, well, was capable, has been tested, of carrying 50 watt-hours per kilogram and has a Young modulus of 10 gigapascal. This, of course, is not mainly structural application, but for example, may replace some panel in the aircraft. Is basically a series of carbon fiber layers. If you touch the center, you may feel the electrode inside. You may feel the cell inside with 4 layers. This is what is inside. If you remove the carbon fiber, please don't. And what's inside here has been tested and is capable of carrying a total load of 120 grams without significant deformation. This is what happened to the sister of that cell of that panel there. 20 of them were put together in a module. So we reached a total amount of energy storage of roughly 7 watt-hour, where the cell, good news, resisted to curing, because of course you have to manufacture that panel. And they provide energy even after being warmed up to 130 degrees in an oven. The tests were mechanical and thermal tests were realized by our colleagues at Aero in France. The daughter of that panel is circulating there, is Matisse. Matisse, we want to be more ambitious, and we wanted to go from a single rectangular piece of carbon fiber to a wingtip for the Pipistrel Vallis Electro. That is this little beast here that is the first full electric aircraft ever certified. Yep. So the module that was created is capable of managing power and delivery, and is capable of self-monitoring the safety of its energy storage component. And this is what we did. Unfortunately, I don't have the sample with me. It's much larger than that. And my colleagues at the moment have it in Berlin at the ELA. So if anyone wants to, has the money to spare a ticket, can go and see it. Still some testing. The developed for tech maturation, of course, are what you may easily expect. So improvement of cell performance, sustainability and recyclability. That's not recyclable, but battery have to be recyclable. Scaling up manufacturing process, structural monitoring, as I already mentioned, multifunctionality in data communication. So battery need to be capable of, I don't want to say self-regulate themselves, but almost. And of course, investigate further synergies with other aircraft subsystems. Okay, this is some other activity. I'm sorry I'm late. This is just some modeling activity that completes our activity. This, for example, is the set of model that we develop. Particularly here, there is a research needs in investigating techniques for data collection, how to get information with the smallest amount of measurement possible, what kind of sensor to use, how to use them, what is the role of machine learning, artificial intelligence in providing safe batteries and possibly getting information that we may not get otherwise directly. Now, yeah, basically, this is some project highlight. If you are interested, they will be included in the slides that Pinar has, so you will receive this. This is just some project that we are involved in, basically battery and development of system for aviation. Sorry for for having taken too long. If you have questions, I'm happy to get them now or later, given that I'm running out of time. If you scan the QR code or if you check them later, just type on internet, you get the link to the center I work in, my working group, and MATIS, that is the project on structural batteries. Thank you for the patience. No, for